Welcome back to Mastering Algorithms. So far, we have learned what algorithms are, what time complexity means, and how to calculate big O from code. But efficient programs don't just use time, they also use memory. Imagine two algorithms that finish in exactly the same amount of time. One uses only a few kilobytes of memory. The other one consumes hundreds of megabytes. Which one would you choose? That's where space complexity becomes important. In this video, we will understand what space complexity is, how to calculate it, and why it matters in real software development. Think of an algorithm as using two resources. The first is time. How long does it take to finish? The second is memory. How much extra memory does it need while running? When we analyzed time complexity, we focused on the number of operations. Today, we will focus on the amount of memory required as the input grows. Both are equally important. Sometimes developers optimize for speed, sometimes they optimize for memory. The best choice depends on the problem you are trying to solve. When we talk about space complexity, we are mainly interested in extra memory used by the algorithm. This includes variables, arrays created during execution, helper data structures, objects, and even the memory used by recursive function calls. One important point, the input itself is usually not counted. We are interested in the additional memory required to process that input. That's an interview question you will hear quite often. Let's find the largest element in an array. Notice something. We use only two variables, max and I. It doesn't matter whether the array contains 10 elements or 10 million. We are still using only a constant amount of extra memory. That's called O of 1, space complexity. The input becomes larger, our memory usage does not. Now, let's create another array that has exactly the same size as the input. If the input contains 100 elements, our new array also contains 100 elements. If the input grows to 1 million, our new array also grows to 1 million. The extra memory increases in direct proportion to the input. That's O of n, space complexity. Whenever you create an additional array or list whose size depends on the input, it's often O of n. Now, let's look at recursion. Every recursive function call is stored on something called the call stack. Imagine calculating the factorial of 5. The function calls itself again, then again, then again. Each call stays in memory until the answer comes back. If there are 5 recursive calls, 5 stack frames exist at the same time. If there are 1000 recursive calls, 1000 stack frames are created. That's why recursion often uses O of n extra space, even when the code looks small. This is an important concept in interviews. Many people calculate the time complexity correctly, but forget about the memory used by recursion. Let's compare what we have learned. Finding the maximum element uses only a few variables, that's O of 1. Creating another array increases memory with the input, that's O of n. Recursive factorial also grows with the number of recursive calls, again O of n. Different algorithms solving different problems can have very different memory requirements. Sometimes making an algorithm faster requires more memory. Imagine storing previously calculated results in a map. Next time, instead of calculating everything again, you simply read the stored value. The program becomes faster, but now you are storing extra data in memory. This is called a time space trade off. Developers constantly make these decisions. Would you rather save time or save memory? The answer depends on the application and the requirement. Imagine you are studying for an exam. Option 1, you remember every formula in your head. You use almost no paper, very little extra memory. Option 2, you write detailed notes for every chapter. Finding information becomes much faster. But now you are using notebooks to store extra information. Computers make similar choices. Using more memory often helps them solve problems faster. During coding interviews, interviewers rarely ask only for time complexity. They always ask what is the space complexity. If your solution creates another array, uses recursion, or stores additional data structures, you should mention the memory requirement as well. Let's quickly revise. Time complexity measures how the work grows. Space complexity measures how the extra memory grows. Usually, we ignore the memory occupied by the input itself. Instead, we count the additional memory created by the algorithm. Whenever you solve a coding question, always ask yourself two questions. How much time does it take? How much extra memory does it use? Now that we have covered both time and space complexity, we have the foundation needed to study actual algorithms. In next episode, we will start with one of the simplest and most important searching algorithms, linear search. We will implement it, analyze its time and space complexity, and understand where it's useful in real world applications. If this video helped you understand space complexity, please like the video and subscribe to the channel. In comments, share an example of an application where using less memory might be more important than being extremely fast. Thanks for watching, and I'll see you in the next episode where we begin our first real searching algorithm, linear search.